So yeah, thanks for joining my talk on real-time adaptive controls for distributed systems. I called it distributed systems because it can be Kafka consumer, it can be any other stream processing consumer. It's basically anything and everything that runs on high-scale distributed systems. So here's what I'll cover today. We'll start with the need for adaptive controls, followed by an introduction to a reference architecture. We'll then discuss the adaptive controls that we have implemented in our production systems, and wrap up with probably a summary and a quick sneak peek into where we are headed next. Before we get into it, a bit about me. I'm Praveen. I'm based in California. My background includes distributed systems, open source contributions, and engineering leadership. If you're passionate about any of this stuff, come and talk to me after the chat. I love to have a conversation. I work for CrowdStrike. If you're not aware of CrowdStrike, we are the company behind amazing Falcon platform. Falcon is probably the first AI native platform out there that helps you protect your endpoints like your laptops, your servers, your mobile phones, cloud workloads, identity workloads, etc. I manage the platform scale teams in APAC and here in USA, and we are responsible for availability, latency, performance, and capacity of the large-scale distributed systems that power these amazing products. Now, just to put things into perspective, here are some stats that speak for the complexity of the challenges that my team faces every day. Our platform communicates with around 80 million peak agents that are deployed on our customers' machines. And these agents are pretty much deployed all over the world. And we handle slightly around 3 trillion plus events every day on an average. So why do we need real-time adaptive controls? As Kafka consumers and producers gain more and more popularity, building for and deploying on distributed systems has turned into a de facto standard for many of these applications today. A direct consequence of this is the explosion of the configuration surface of these applications and services. So much of this configuration include tunables like your worker pools, your auto-scaling policies, how do you retry, how do you back off, etc., which are often about service resilience. Finding the ideal initial values for these tunables require deep technical expertise. Also, these workloads change over time, right? So this requires regular effort to retune all of these configuration parameters. And as a consequence, some of them might get stale if we don't configure them properly, or the workloads might have changed. And configuration errors have become a source of operational toil and one of the major causes of incidents and cascading system failures across the industry. We wanted to better than static configurations where we can. So we sought to automatically identify a system's inherent ideal configuration in a way that would require no manual work, no centralized coordination, and hence no single point of failures. Infer the limit without any knowledge of the hardware or system topology, because that is oftentimes outside of the control of development teams. Adapt to changes in system topology, because change is inevitable and easy to compute and enforce. I'll introduce a very simple reference architecture to anchor our discussion. We have two services here, a writer service that consumes from Kafka and writes to a persistent store, here Cassandra, and a reader service that reads and processes data from Kafka. The actual technologies doesn't really matter here. We are talking about the mental models that we use to model capacity of our systems. Now let's talk about various controls that are in place to make these services more resilient. We'll discuss the challenges of traditional controls by going through example scenarios, which are hypothetical, and conclude by introducing the adaptive variant of each of this control or pattern. Let's start with circuit breakers. If you don't know what a circuit breaker is, it's essentially a simple control that acts as a proxy for operations that might fail. So it decides whether to allow or fail an operation based on recent performance. In the context of our writer service, a very simple implementation of a circuit breaker could look like this. We have a token bucket that gets filled every t minutes. When the writer service encounters a failure, it consumes a token, and if there are no tokens left, it opens the circuit and starts rejecting messages without attempting a write. So this circuit will be closed once the bucket is refilled, and it goes on and on. This control is very simple to understand, very common across many services and applications today, and easy to maintain, but presents some interesting challenges that might come with scale. Now let's imagine that this writer service is handling multiple tens of millions of writes per second. Little fun fact here, at CrowdStrike we actually have a service that sort of resembles this, which handles 100 million plus writes per second. So at that scale, it's very easy to hit the limits of technologies like Kafka and Cassandra or what have you, right? This is where cell-based architectures and help us come very, very handy and help us scale beyond the limitations of the underlying technologies. The idea behind these cells is very simple. Each cell is an exact functional replica of each other, and request set is sharded basically across the cell dimensions. Coming back to the drawbacks of our simplistic circuit breaker, the problem that we have here is of twofold. First, traffic distribution could be uneven among these cells for various reasons. Maybe one cell is bigger than the other. Maybe one of the cells is undergoing maintenance. And traffic distribution could be dynamic as well. We might add new traffic, redirect existing traffic, etc. So configuring the right amount of failure tokens will slowly turn into an operational nightmare. You'll get paged a lot. People who you put on call will leave your company, and essentially, it will be a mess. So how do we solve this? How can we make this adaptive? Simple, instead of basing the circuit logic on failure tokens, we base it on a percentage threshold. And just by doing that, we are adapting to the traffic size, and irrespective of how many cells you have in your company, you have one standard way of defining circuit breaking policy across all of your consumers. The simple technique might just sound like common sense, because it really is. But I'm including this in the talk because it provides a nice mental model for moving away from static configurations that are pre-configured and towards responding and adapting to stimuli at runtime. This simplicity comes with limitations though. The circuit breaker here that we just saw is global at the level of a consumer, and it lacks granularity. So bad data from one dimension, like a customer, a machine, a message type, etc., can cause the consumer to fail beyond the configured percentage threshold and can cause head-of-line blocking if not dealt properly. Obviously, it is very generic and lacks adaptivity to traffic shape, as we just discussed, and this can cause inefficiencies for some high-throughput Kafka consumers. So we improved upon that by using probabilistic data structures called sketches. Sketches are memory-efficient algorithms to summarize large-scale data streams. This allows the system to circuit break on various dimensions like customer IDs, agent IDs, message types, etc. So we can have billions and billions of message keys, but we still are using a very memory-efficient structure to handle tokens for each particular dimension. So this helped us achieve fault isolation for our customers while also preserving the average throughput of our system. Now let's talk about another simple and well-understood control pattern, backoff. We'll start with another very simple implementation and work towards making it adaptive. Here, the writer service is configured to sleep some amount of time if number of failures over a particular period of time is greater than the threshold. The idea here is that by slowing down the service and by making it sleep before it picks the next message from Kafka or next batch from Kafka, we are giving the downstream some time to recover. This is super simple, but it has the same problem that our simple circuit breaker had a while ago, especially when we are running this at scale. We know how to adapt for traffic size now, so let's make that modification. So we've modified the sleep logic to sleep not when we exceed a pre-configured amount of failures over a period of time, but when a percentage failure rate exceeds a business-driven threshold, right? Now, thanks to this simple update, we are adapting to traffic size. But can we do better than this? I think we can. Let's make it adaptive to the feedback shape from our downstream. Here, we introduce a couple of components in our architecture. First, we have a component called error reactor, which provides weights for each kind of failure and default weights for errors that we expect from our downstream. It also defines the weight that is associated with successful acknowledgements as well. Second, we have a throttle controller that observes the results from the processor and calculates a simple exponential average using the weights from the error reactor when a particular type of failure happens. So this gives us the ability to back off not only based on size, but also enforce varying levels of aggressiveness in our back off strategy. Let's say we want to back off just a little when one of our latency SLAs is exceeded, and back off a lot more when we observe timeouts, and back off even more when the downstream is completely down. All we need to do is define these failure modes in the error reactor, and the throttle controller will just do that for you. And the recovery will be driven by the amount of success messages which carry a positive weight, and the decay over the previous negative weights from respect to errors from the simple exponential average, if you're following, would help us achieve that. Before we move on to our next control, I think it is important to understand when backoff works. So is it enough by itself? Is it enough to prevent overload and cascading failures? Unfortunately, the short answer is no. This code that I found on the internet says it all. The only way to deal with long-term overload is to reduce load. Deferring load, which is what we often do with backoff, doesn't really work all the time. I would like to emphasize reduce total work here because I think it is a nice segue into our next control. Retries. Retries can increase load and bring an amplification factor that oftentimes is not trivial to capture. So retries are often thought of as an essential component of resiliency control, and in fact they are, but they ensure a message eventually gets processed when there are transient failures in our systems, right? However, there is a hidden danger with retries. Retries can lead to amplification, as I just mentioned. So retrying too aggressively creates more load, worsening the original failure. So let's take a quick look at this diagram. It shows a retry controller that injects the retry count into the message processing pipeline. As the process message step occurs, it's observed by an error reactor that tracks whether retries are actually needed for this particular type of message or failure. And the retry controller ensures that only a certain number of retries are attempted, balancing resiliency and avoiding overload. So by controlling retries adaptively based on system's health and observed errors, we can avoid turning resiliency into a failure amplifier while still ensuring fault tolerance. Now let's talk about concurrency. Let's zoom into the writer service that we have from our reference architecture. Each writer service here is an instance of Kafka consumer, which has multiple workers in it and a worker pool, of course. This worker count is configurable as well, like any other worker pool. We configure this to a predetermined number of workers when we deploy a new service, new consumer, and also update this from time to time as per need, this is the common SDLC lifecycle for operations of a Kafka consumer looks like, right? Now let's go through some scenarios to understand the challenges with having a predetermined fixed number of workers. In this scenario, the Kafka topic is pretty much empty, and the workers are not doing any work other than just polling Kafka for new messages, and are just potentially wasting CPU cycles. Now say we have some traffic. Cassandra is in good shape, which is our downstream in this example, and the consumer is performing quite well. But since we are running the same number of workers as we are when we are empty, maybe we are potentially not utilizing all the processing capacity that is available for our consumer. Maybe we can run more number of workers in our worker pool without overloading the system. Now let's say that Cassandra, which is our downstream here, is exhibiting downgraded performance. But given that the worker pool size remains static regardless of the feedback from downstream, this might lead to amplification of failures and lead to cascading errors. Surely backoff strategies would help here, but is backoff alone sufficient? How is it related to the concurrency of our service? Before we answer that, I want to take a quick detour and talk about queuing theory. Little's law in particular. So Little's law is a theorem that determines the average number of items in a queuing system based on the average waiting time of an item within that system and the average number of items arriving at that system per unit of time. Now let's see if we can apply the principles from this law to model the processing capacity of writer service. Now we can clearly see that the number of workers is synonymous to the arrival rate from Little's law, as the number of workers influence the arrival rate of messages into our system. I mentioned a couple of slides ago that backing off can help in the case of overloaded system. But now, thanks to Little's law, we are able to see how that is related to the concurrency of our system. This illustration helps us come up with a mental model to understand the interplay between back-off and concurrency strategies and how both together can influence the total capacity of our system. Let's say our back-off strategy is to sleep sometime before picking the next message from Kafka. Backing off can increase the average processing time. And the concurrency of the system, number of workers in our example, if you remember, can influence the arrival rate of messages. If you are following closely, you will identify the underlying theme that we're trying to capture here is that capacity is not a constant. The capacity of your services downstream systems might change over time. And here, there is a need to change the processing capacity of our service as well. Concurrency combined with appropriate back-off strategies is a great way to do that. So if the capacity doesn't remain constant, how do we estimate the right number of workers? Not only that it is hard to estimate the right number of workers for every given day and every given scenario, it would be an operational nightmare if we were to keep estimating this again and again and update configuration periodically. Instead, we can infer that based on the feedback from downstream systems and change this dynamically in real time within permissible bounds. The beauty of this is that the ideal capacity doesn't need to remain constant. As the ideal capacity changes, the feedback from the downstream system changes, and we adapt accordingly and eventually converge with the ideal capacity. There are many strategies using which we can adaptively change the concurrency of our services. Majority of this adaptive configuration management theory took its shape through TCP congestion control. We wanted to start with the simplest of all, experiment with it in our production and see how it goes. So we picked the simplest TCP congestion control algorithm, which is AIMD. The additive increase and multiplicative decrease AIMD algorithm is a feedback control algorithm, best known for its use in TCP congestion control. AIMD combines linear growth of the congestion window when there is no congestion with an exponential reduction when congestion is detected. In our scenario, we can model congestion using the write timeout to the Cassandra data store. Here, we can see adaptive concurrency in action. As the Kafka topic is receiving more and more traffic, we see that adaptive concurrency increased the number of workers of a consumer in a consumer group in the writer service to match this demand. And once the lag was consumed, the worker count has reduced because there's no work to do. And this saves CPU cycles. This is another example where adaptive concurrency has really been a game changer for us. As opposed to the previous example, the number of workers have not increased initially here, even though there is significant spike in traffic. This is because the adaptive worker pool noticed that there is an elevated latency from Cassandra downstream and avoided overloading the system. And when the latency was down to normal ranges, it automatically increased the number of workers to bring the processing pipeline up to date. All of this has happened in real time without any manual intervention. Now let's take a look at rate limiting. We will use the reader service from the reference architecture that we just saw before to help put things into perspective. Please note that the rate limiting here that we are going to discuss is consumer or client-side rate limiting and not the one that's enforced on Kafka broker side. Traditionally, rate limiting is done through centralized coordination, using a fast in-memory store like Redis to host the rate limiting configuration. Like it can be a token bucket algorithm or anything similar. Clients make requests to readers, and readers, upon receiving these requests, will go and check the central store to either allow or reject a request. Again, very traditional. Also, it is not uncommon to use a local in-memory store in the reader containers that periodically update the config from a central store. Both of these designs require central coordination and have single point of failures, especially when the central store is down for extended period of times. Even if we ignore the coordination problem here, there are still some shortcomings with traditional rate limiting. Let's go through a few scenarios and see if we can surface them. The first scenario is as follows. Say the reader consumer is reading from 3 topics, A, B, and C, and the request rate allocation is 10 requests per second to A, 25 to B, and 5 reads per second to C. Let's say if one reader container can serve about 100 requests per second at any given point in time. With this allocation strategy, we are only using 40, even with peak usage. We are unnecessarily rate limiting clients when we can process more of their requests, so we are essentially wasting capacity here. Now let's take a look at another scenario where we have reader consumer scheduled on a busy node and is getting CPU throttled, for example. The total capacity will not be 100 nav because the container or the consumer is struggling to get some CPU time on this node. But with a static configuration for our consumers, consumer groups will still allow 40 requests per second to flow through our system. This will lead to resource exhaustion, eventually lead to latency spikes, consumer group lags, memory leaks, and all that sorts of fun that is only too familiar for us. Finally, in this scenario, we challenge the fundamental assumption that we can guarantee that the consumer can process 10 requests per second from A, 25 from B topic, and 5 from C topic. For example, when Cassandra is exhibiting downgraded performance, we won't be able to serve that many number of requests. But the consumers of A, B, and C will keep making requests and keep hammering Cassandra, and these requests won't get rejected by the rate limiter that we have in the consumer because they are within the limits, and it gets really hard from there. So the idea here is without load shedding, we will eventually end up with cascading failures. So how can we improve upon this? Following the theme of this talk, we respect that the capacity of the system doesn't remain constant and adapts to its changes. Let's see how we can do with respect to rate limiting. The idea here is instead of allocating A with 10 requests per second, what if we allocate A with 25% of the total capacity? And we do similar allocations for B and C as well. But what about T, the total capacity of the reader consumer? How do we estimate that? It is simple. We do not estimate that. We infer that from the system. This is the same approach that we use for determining the number of workers of our writer service. We start with a seed, a max, and a min value. We let the algorithm converge around the ideal value of T for that particular point in time by adapting to the feedback of the system. So this adaptive rate limiting system requires no manual work, requires no centralized coordination, easy to compute, and will not steal resources because it's just calculating floats, infers capacity limits without any hardware knowledge, and will adapt to changes in downstream dynamically. Next up is autoscaling. Traditionally, autoscaling for Kafka consumers is based upon two different dimensions. Like in the first is resource allocation metrics, like CPU usage, memory usage, or second, external metrics like incoming requests or consumer group lag that we get from a system like Burrow or some other form of monitoring. This usually works great for stateless services or services that have no downstream dependencies. But the issue with that autoscaling system is what I'd like to call that as an open system. It only takes the load that is coming into the system into account and doesn't necessarily respect the feedback from the downstream. And that is problematic because it would lead to potentially overloading downstream And in the example that I have here, we have a Kafka consumer group lag-based auto-scaling strategy for the writer service. Because there is more data coming into the topic, the writer is falling behind, the autoscaler will just blindly keep adding more pods until it maxes out. And this is detrimental to the health of the system overall, as the downstream is already under pressure and could not potentially work with all this extra overload. So how can we improve upon this? Following the theme of this talk, we respect that the capacity of the system doesn't remain constant, and we adapt to its changes. Let's see how we can do that with respect to autoscaling. So let's say we are using adaptive concurrency with the following configuration. We have maximum number of workers as 5, minimum number of workers as 2, and we have an autoscaling rule that says scale up when this utilization is greater than 70%. So say for 10 minutes, and scale down when the utilization of the worker pool is less than 50% for 10 minutes. Let's explore a few scenarios that will help us understand how adaptive concurrency can build an adaptive autoscaler. Imagine a scenario where we have 2 pods, each with 3 workers in it. The average capacity in this scenario is 60%. So as per our autoscaling strategy, there is no need to scale up or scale down here. But when the system is idle and there is no work, the adaptive concurrency will reduce the worker pool size to save resources, as we have seen before. In this scenario, the average capacity utilization is 40%, resulting in a scale down. Next, when a spike of traffic comes in, we have the system lagging behind as it is under provisioned. So there is a lot of work coming into the system. Adaptive concurrency sees this, increases the worker pool size to, let's say, 4 workers. The capacity utilization will reach 80% now, resulting in a scale up, as it is higher than our scale up threshold of 70%. Now that we understand the simple math behind this adaptive capacity utilization, let's see how we could leverage this for an autoscaling strategy by looking at hypothetical series of events. At the top of the screen, we have 1 pod with 4 workers in it. The utilization in that case is 80%, which is greater than 70%. So our autoscaler will notice this and adds 2 more pods. So now we have 3 pods with 4 workers each. And let's say this is too many workers, and we are overloading Cassandra at this point, which a traditional autoscaler would normally do. Cassandra's performance will be degraded, we start receiving errors, but the adaptive concurrency controller in our consumer will adapt to this and reduce the number of workers in each pod to, say, 2, which is the minimum configuration. But when we run with 2 workers for some time, our capacity utilization will be less than 50%. So the autoscaler will scale down the deployment by 1 pod. So now we have 2 pods with 2 workers each. Since this is too low, it gives Cassandra ample time to recover by reducing the overall load on the system. And when the success rate is high, adaptive concurrency increases the number of workers again, which would then trigger the adaptive capacity calculation again, and we'll have more pods. And say, as an example of in this hypothetical scenario, we'll converge at 3 pods, which is stable for that point in time. However, there is one last challenge here. At the heart of this autoscaling strategy is the maximum number of workers for a particular consumer. How do we estimate that? So to determine the optimal number of workers in our system, we looked back at academic research on system scaling, particularly how throughput is affected as the number of workers increased. The main idea here is to establish the relationship between the number of workers and throughput through controlled experimentation under ideal conditions. This allows us to estimate the theoretical maximum throughput. So we'll start with the myth, which is linear scaling. The myth of linear scaling suggests that adding workers will increase throughput linearly, which is never true in most cases. However, this rarely holds true. And in reality, based on Amdahl's law, throughput increases to a point, but eventually hits a plateau, which we call the performance equilibrium. At this point, adding more workers is actually detrimental to the performance and yields diminishing results. However, if we keep adding workers beyond the equilibrium, we risk retrograde performance as seen in the other graph, where throughput actually decreases due to the increased coordination overhead and contention among workers. This represents the universal scalability law. So what is the takeaway here? With these models, we can experimentally identify the point where throughput is maximized, giving us a theoretical maximum worker count. In practice, we can take a safe threshold, say 80% of this theoretical maximum as our practical ceiling to ensure stable and reliable performance without pushing the system into overload and retrograde behavior. When we launched this in production for one of our large-scale deployment, we were able to achieve around 40 to 50% reduction in compute resource usage and has resulted in significant improvement in stability by contributing to fewer incidents and alerts and all that fun. When we started working on the idea of building adaptive controls that respond to real-time feedback, it's clear to us right from the beginning that this is going to be a marathon and not a sprint. So encouraged by the initial results, we have seen, we put together a roadmap that my team is currently working on and will continue to work on in the near future. I want to share some of those plans here to give a sense of where we are heading next. We are working on improving the reactivity of our adaptive concurrency algorithms. While AIMD is simple to understand, implement, and run, and has given us excellent results so far, there are some drawbacks with AIMD. It is essentially loss-based congestion control algorithm. So the risk with AIMD is that it will switch to congestion avoidance by decreasing the concurrency exponentially, if you still remember, only when it detects loss, which in our case is timeouts. Another drawback, in my opinion, of loss-based algorithms is it will continuously oscillate the system between full utilization and underutilization to a degree. In our case, we restricted this amplitude of these oscillations by using minimum and maximum bounds. We actually first started without having those min and maximum bounds and quickly ran into this problem. And to fix that, we started putting those minimum and maximum bounds. And there is another algorithm called slow start threshold algorithm. Unfortunately, I don't have enough time to get into the implementation details here, but we are using that to reduce these oscillations as well. But if you are actually interested in the implementation details, a member of my team has presented this at greater detail in Go4Con. So I encourage you to go and check out this talk on YouTube, and it will explain you how we actually implemented this system. On the other hand, we have delay-based congestion control algorithms that react to differences in round-trip delay time over a threshold being exceeded. So the advantage of delay-based algorithms is basically they achieve better average throughput since they can keep the system around full utilization. We are working on two such algorithms. They are called TCP Vegas and gradient descent, if you are aware of TCP congestion control algorithms. But basically that, we are trying to move our system from a loss-based detection system to throughput-based detection system. Remember the adaptive rate limiting strategy we discussed before? It works amazingly well when the reader consumer has one downstream dependency, like a single database cluster as shown here. It is both fair and greedy when appropriate and helps improve the overall throughput of the system. But this system actually has a pretty significant drawback. Now imagine if the reader consumer is actually communicating with a sharded data store. For the sake of simplicity, let's say we have three consumers, A, B, and C, and they make requests over specific key ranges that are distributed across these sharded data stores. The adaptive rate limiting algorithm will still work nicely as long as all the downstream shards are all healthy or unhealthy at the same time. And if one of the shards is overloaded or underperforming for whatever reason, the adaptive rate limiting algorithm will respond to this feedback and bring down the total capacity of the system. Now this is bad. In this example, even though client A never makes any calls to the problematic shard, it will still lose its allocated capacity, and this could result in underutilization as we are clearly rejecting requests that we shouldn't. We are working on an improved adaptive rate limiter, which will fix this problem by partitioning the capacity using the same probabilistic data structures that I talked about before. But before I conclude, I'd like to briefly introduce another use case for dynamic adaptive controls. This one is slightly outside the resiliency domain and focuses more on the performance and efficiency. Specifically, I'm talking about adaptive cache management. So the problem with traditional caching strategies that are in place today is no single statically configured cache management policy consistently yields the best caching outcomes, because the workloads will change over time and the performance can significantly depend on how the application is actually accessing data. And the challenge for developers is this: finding that best caching policy for a given system requires careful analysis of workloads, testing different cache strategies, and setting the right caching strategy. But as we have seen throughout the tenure of this talk, that capacity doesn't remain constant, the workloads might change over time, the system topology can change over time. So it is very, very hard to predict in advance what would be the best caching strategy for any particular service. So we are exploring a new idea called dynamic adaptive caching. So basically what we'll have is we will have two buckets, one for recency and one for frequency, and adjust the nature of this adaptive caching policy to favor one bucket for some time and the other bucket for the other time. So essentially we change how much LRU we want and how much LFU we want over a period of time. There is a lot of academic research out there, which talks about this. Especially there is an algorithm called hill climbing algorithm that we're using to implement this as we speak. I encourage you to explore these approaches further, as they can significantly improve performance of your systems in various scenarios, not just streaming. To summarize what we have discussed today, essentially, I want you guys to take away these as key takeaways. We can adapt to feedback from downstream systems and change the concurrency or processing capacity of our system. We can utilize relative capacity thresholds where it is possible, instead of relying on static configurations like 5,000 errors per second. We can make closed-loop auto-scaling decisions based on adaptive concurrency if we have that in place. By monitoring system health and reacting to real-time conditions, these adaptive controls ensure we have fault tolerance and prevent the system from turning small issues into amplified failures. I hope I've given you enough motivation to move away from static configurations and move towards adaptive controls that require very little manual intervention. If you want to work on awesome distributed challenges like this, check out our careers page or come talk to me. I'm actually hiring managers and engineers both across APAC and USA, so please come and talk to me. That's it, thank you.